Hi everyone, this is Mr. Robotic Warfare, and in this video I wanted to do a deep dive on the design that I showed off in my previous video, that being the 8-bit Parallel Prefix Adder that doesn't use any redstone dust. So that's what you're looking at right here. And what I wanted to do is take an opportunity to not only describe how this actually works in more detail, but also detail a little bit of the design process and the way that I go about making the decisions for some of these things. So for example, I've got a lot of additional test devices over here that I wanted to briefly walk through and just show you what the development process looks like for me for something like this. So for starters, I've set up a little area over here, which is going to help us step through the different pieces of what this is doing here and how it works. It'll let you see it a little bit more detail. But the other thing that I'm going to be using is this wonderful lecture from ETH Zurich. And what I'm going to be using it for is to essentially explain to you how adders work and how these different things happen. I've found this as a resource. I've actually referenced this multiple times myself for the course of building this, and I think it's a really fantastic, concise lecture on how adder architectures work. So what I'm going to be doing is I'm going to be talking a little bit from the lecture, and then we're gonna switch back over to in-game, and I'm going to show you how some of these things line up. So let's just start with a ripple carry adder, right? Roughly what a ripple carry adder does is that you take two binary numbers, A and B, you have some kind of carry input, and what you want is you want the sum of those two numbers, S. And then also, if you have a carry out that's generated from that, that's going to be something that's also sent out. So when you look inside of a ripple carry adder, right, these are just two generic numbers, A and B. What you're actually going to find is a number of individual modules that are chained together, and these are called full adders, or FA. And what a full adder is it essentially does this calculation for only 1-bit numbers. So you can see A0 and B0 here are the smallest, the least significant bits of numbers A and B respectively. So this is either a 0 or a 1. This is either a 0 or a 1. Same thing can be said of these two things right here. So these things are all either 0 or 1. And what this operation is essentially going to do is to compute the sum and the carry out. So the curse of the carry here is that when we do this process with these full adders, right, the calculation of this second full adder is dependent on the carry out of this first one, which means that necessarily this computation has to finish first. So what happens is that to actually get all the way to the end of the machine, you can see here it says that we need to do n+1 stages of calculation before we can actually get to the final bit of our sum and therefore find the result. So it said in other words, the carry has to propagate all the way from the least significant bit, which is all the way down here, to the most significant bit. And this is the critical path of the machine, which means that we're essentially looking at the worst case scenario. So this is not always going to happen, but it's going to happen a lot of the time. And now this is actually a good place to segue back in. I'm going to hop back over to the ripple carry adder that I showed off in a previous video. And what you'll see is that based on, excuse the lag spike, based on what you saw previously, we see exactly this here in Minecraft as well. For the full critical path of the machine here, this is taking 44 game ticks. But for any individual calculation, for something with like just 1 bit, it's going to be somewhere in between 16 game ticks and 44 game ticks. So the idea is that it's not always going to be as bad as the worst case, but still when you're designing something like this, you have to worry about what that worst case is. So once again, we are kind of re-going over what the full adder logic does. We have the diagram right here, which is essentially the logic diagram, as well as the Boolean operators that are being performed here. And we see this in game as well. If you remember, I basically drew up this schematic as a pixel art. And what you can see here is essentially what's reflected. It's just drawn a little bit differently. So you have the two XORs in line and the two ANDs in line with the OR kind of on the side here. And the way that this one is drawn is essentially to emphasize the fact that you've got the carry in coming in from one side and the carry out coming in from the next side. Here you can see my cursor now. You got the carry in coming in from one side, the carry out going from the other side. So you can imagine kind of pulling and tugging on this and you would get something that looks like the same shape. So let's actually talk about what's happening, because we've created two intermediate points now. we're not just dealing with the full adder, we're dealing with two other signals now, which we're calling P and G. So that stands for propagate and generate. And that's what we were talking about here. So if we're looking at an individual full adder, we are either going to propagate a carry or generate a carry. A carry is generated when both A and B are 1, right? So if A is 1 and B is 1, we're generating a carry no matter what, right? Because a binary 1 plus a binary 1 is a binary 1, 0, which is 1 plus 1 equals 2, represented in binary. 1, 0 is a 2-bit binary number, and this full adder is only operating on 1 bit, which means that we need another bit of representation, which means that we need to carry that bit out to the next stage so that it's actually going to be able to be represented. So regardless of what the value of the carry in here is, regardless of what the value of the carry in is here, you're always going to generate a carry. So the Boolean operation that we do is the AND operator, so A and B, which essentially says if the output is only 1, G is only 1 if both A and B are true or are 1. On the other side, if only one of them is true, that means that if we have a carry that's present, if we have a carry in that is coming into the machine, and one of these two is a 1, that means that we're going to propagate this carry to the carry out, right? Because when we generate a carry, that means that we have 1 plus 1 somewhere, and we're essentially adding 3 numbers when we're doing a full adder. We're adding A, B, and the previous carry in. So that means that if one of A and B is true, or 1, that means that we are then going to propagate that carry. And interestingly enough, we have to do this with the exclusive OR operator right here, because if they are both true, if A and B are both true, we're already going to be generating, which means that the concept of propagation doesn't really apply as directly in that scenario as opposed to when only one of them is true. So then, if we summarize this and look back at the diagram and we say, okay, our generate signal is defined by A and B. Our propagate signal is defined by A XOR B. And then in the same way, our sum, our final output for that bit of that full adder, is the propagate XORed with a carry in, which you can see happening right here. And then we have the carry out from the next stage is the generate or the carry in and the propagate signal. So this is literally what we just described, right? We're going to generate a carry if either our generate signal is true or we generate a carry via propagation of the previous carry. And once again, that's an AND operation because both of those things need to be true. So now that we've established this, the idea is that because that critical path is very slow, we want to find a way to speed this up. And there's a couple of different ways that we can do that. I'm not going to go through all of these, but I just want to use this as a theoretical framework for what we're actually going to be looking at here. So there are a couple of different ways that you can do this here, which use some clever muxes and stuff like that. But what I want to look at here is the carry lookahead adder. So as we said earlier, when we were all the way up here, what's happening is that to get the next sum bit, we need to know what's actually happening with the carry of the previous stage, right? That is an inescapable fact of what we're doing. However, it's possible that we could do all of this logic out front because we saw that these signals are essentially just logic expansions, right? So if my CO, or my carry out from the previous stage, is my carry in to the next stage, you could just imagine replacing that with this expression from the previous stage. So let's just do a quick example here. If I'm looking at the second bit, my sum is going to be propagate XOR carry in. And my carry in the second bit is going to be the carry out from the first bit. So you can imagine this as being P XOR G from the previous stage, or CI from the previous stage, and P from the previous stage. So we can continue expanding out. And what we do with a carry lookahead adder is we're actually doing exactly that. So for each sum bit, you need to know what the previous carries are. So we can do this faster than the traditional ripple carry structure by just doing all of this calculation at the same time. So that first carry is going to be your carry in. The next carry is going to be the generate or. So the plus here is the or operator. It's shown in two ways in this diagram. It's either with the pipe or with the plus. But you can see this is exactly what we had written previously, right? We see G, or, CI, and P, and we're looking at the same thing. Oops. A little bit of things to come here. So we're seeing the same thing here, G, or P, and C. Okay, but like I said, we can actually do this additionally. So if we take that expression and we substitute it in the next one, what we see is G1 or P1G0 or P1P0C. And you can see that it kind of continues getting bigger and bigger and bigger. And you can continually do this, and you can get all the way to your 4-bit representation or your 8-bit representation, etc. And then you take all of those things and you XOR them with the original propagate signals. And that's what actually gets you your final calculation. And I also built that same kind of thing here. So this is another one of the designs that I've showed off, which is a carry lookahead adder. So I think it'll be easier to see on the 4-bit version. Unfortunately, the metadata on the signs did not copy over, but I had actually, when I built this, does this one have them? No, unfortunately, they're missing. But what I had actually done was I had labeled each of these things with what they were actually calculating. So I guess this one is a little bit cleaner over here. So what we're doing in this machine right here is we have our A input right here, these 4 bits, and we have our B input, which is right here. And we're doing those first 2 operations, right? Because if you remember, the generate is A and B, and the propagate is A XOR B. So this right here is an AND gate. This is a Redstone block AND gate, which I use fairly frequently. And this is my XOR gate. So what's happening here is that these 2 signals are getting ANDed together. So basically, if both of the signals are present, these 2 redstone blocks are going to get retracted, and this line is going to turn on. So you can see that we have our 4 AND gates here, which give us our 4 generate signals. And then we have 4 XOR gates here that are XORing A and B for each of the bits, which gives us our 4 propagate signals. So this is all of our propagate signals, and this is all of our generate signals. And now what we're essentially doing is using that information to then compute all of the carries. So if we just jump back to the slide here, you can see that just as an example, the first carry bit there is going to be G0 or P0 CI. So if we look at, let's see if I can remember how I built this thing. That would be a real trick, wouldn't it? It's probably going to be right here. So one of these signals here is coming from each of these observers. And in fact, we can just talk about this generically. You don't need to give a specific example. But the idea is that each of these signals are being fed through by different observers in different locations. And each of these right here are essentially AND gates unto themselves. They're multi-input AND gates. So in the same way that this guy has 2 of these horizontally to constitute the AND gate, this has the same thing in more or less the same direction, but you can see that I've actually swapped it here. So what's happening is that each of these things horizontally in a slice like this are an AND gate, and we are using each of these signals very methodically to then input that into the correct AND gate, and all of those AND gates are being triggered here. And then from there, as if you can see, if you remember from the slide here, we can see that we're ORing all of these things together, right? We have these different individual expressions. This is, I believe it's called a canonical sum of products form, which means that we have each of these things that are being ANDed together, and then we're ORing a whole bunch of things that are ANDed. So in Minecraft, what this looks like is taking the output of these AND gates and then just chucking them onto a rail here and having multiple outputs of these AND gates all go onto the same rail here, with these 2 things obviously being synchronized. And then you just take the generate signals and you OR them accordingly. So when we actually do a calculation with this machine, you would see a generate signal go down this way, continue on, and come up. And at the corresponding moment, an AND gate that would trigger, if it does trigger, would also energize these lines. Then, because we're doing carry calculation kind of offset, so you can see that from this first expression here, carry 1, or C1 there, is G0 plus P0 CI. So we're using the previous bit, or the previous information from the previous bit in our calculation, which means that when we go to XOR these with the output, we're actually going to be off by 1 bit, right? Because this is essentially P0, P1, P2, P3, But down here, what we've actually got is C1, C2, C3, and C4, which is our carry out. So what this guy does right here is this is essentially shifting the signals over by 1 so that we can actually do the XOR properly. So this, let's see. This signal here would be the carry in. And you can see that, oh, I keep doing this, man. When we have this observer right here, which is C1, it's going to power, oh, excuse me, I'm on the wrong side of the machine. So if this is our carry, in right here. If this is C1, C2, C3, C4, that is then going to propagate to this rail, shift over by 1, go into that observer, and then come up and realign itself in the next bit here so that I can be XORed with the correct propagate signal. And that's what actually gives us our output. So carry lookahead is also something that can be done here. But as you can see, for larger number of bits, because we have all of these different signals that we need to contend with, our busing for these signals becomes incredibly complicated. Although there is a nice symmetry to it, you can see that a lot of these observers just kind of go down the line because what we're essentially doing is we're doing multiple calculations multiple times. So in fact, these signals here are being duplicated multiple times. So I'm recalculating the same quantities multiple times because that's how it actually can fit in the machine here. It's actually in the middle of a calculation, you can see. But the idea is that to actually do this properly, you need to calculate these quantities a bunch of different times, which means that you need to have them bust multiple times and you need them to be accessible in the correct way so that you actually create your output. And this is very space inefficient, especially with this kind of design. So we continue to search for a better architecture to do this kind of addition. Where is my button here? So that brings us to parallel prefix. So let's explain how that works a little bit now. So what is parallel prefix? It says on the slide here, represents a systematic approach to designing optimized adders. Now, is that to imply that other things are not systematic? No, but we have a much greater flexibility with this in specific to what we can actually do. So parallel prefix adders are separated into 3 broad stages of computation. You have the pre-processing, which you've seen on most of these machines, the carry propagation, and the post-processing. And this is actually fairly similar to everything that we've seen thus far. You can think about it this way, right? So this is right here, the pre-propagation, or excuse me, the pre-processing are these 2 gates right here to get these signals. Then the actual carry calculation is essentially happening right here. And then our post-processing is just calculating the output. So we've done this before, but it's just going to take on a little bit of a different way of looking at it. So once again, the different kinds of adders differ only in the ways that the carry propagation is calculated. Pre and post-processing is identical to everything that we've been doing before. So if we are really reductionist about this, what does that mean? It means that we stick an XOR gate and an AND gate at the start and an XOR gate at the end. And that is more or less what we take. So here is this kind of represented in a diagram, right? So we take our different half adders here. So previously when we talked about this circuit right here, this thing is a full adder, but we call this just group of 2 gates right here, we call that a half adder. You'll notice that it says that the first one is a full adder here because we've got the carry in. That's a little bit of a caveat that we'll get into later. But you can see the same kind of thing. We have our half adders that are creating our propagate and generate signals. We do some kind of carry propagation in the middle. Then we shift it over by 1 bit, do a final XOR, and that's what actually gets our sum. Now, once again, the important thing to note is that you're going to be using the generate and propagate signals in the carry propagation calculation, right? You're going to be using both of those things. But the output that's used is only the generate signal. When you do this final XOR, you're using the initial propagate values, which you can see in pretty much all of the machines that we've looked at so far. It's easiest to see on the CLA. So you can see that we're doing all of this calculation and we're using these propagate signals, right? These propagate signals are coming out of the XORs on the top here. So we're using them to actually do stuff here. But at the same time, those signals are all making it back to the end so that it can actually be used in this final XOR. So even though we're using these signals in the middle, we have to use the initial ones when we're doing that calculation. So how does parallel prefix differ from what we've been looking at so far? Well, like I said in the showcase video, while a ripple carry adder is doing everything sequentially, right? You're doing it one right after the other, and you have to wait for everything to go on. And carry lookahead is doing everything all at the same time. What we want to do is we want to find some middle ground of those two things, which is finding a systematic way to compute those carries by doing some of it at a time. And what you get when you do that is parallel prefix. So we can now talk about something that are combined propagate and generate signals. Now, I personally didn't find this concept super helpful when I was first learning about parallel prefix, so I'm only going to skim it briefly, and I'll explain everything that you need to know. So the idea is that at any given stage, we have our generate and propagate signals that are available to us. And for any given point, we can say that we're confident in what those values are going to be, right? Because the generates and propagates for the individual things are calculated at the start. But as we go on, if we're going to try and do this carry calculation as we go, there's a chance that we might want different values to represent that information. So the initial propagate signals are written as essentially the initial things that we have, and we want to calculate all of the generate and propagate signals so that we can then use them to calculate the final output and the carries at the same time. So there are two distinct parallel prefix operations. The first is we're taking the generate and propagate signals from one bit and the generate and propagate signals from the previous bits, might be more than one, and we are merging those ranges together so that we get something that's representative of the entire range. So if you can think about the way that it's listed here, you take bits from I to j and bits from j minus 1 to m, so two consecutive groups of bits, right? So let's say that this is a 4-bit number. This would be bits 0, 1, and then 2 and 3. What we want to do is we want to then combine them into a complete range of 0 to 3 with everything being correct. And this is actually the stage in which we're doing this logic. So you have these two inputs and you see two outputs here. What's actually happening is that these are the same output right here. This guy and this guy are the same thing. We're just sending that output in two different places, right? Now, the other thing to note is that this is the process that's happening for both generate and propagate separately. There's different logic going on for these two things. So at each stage here, you have essentially 4 inputs. You have generate and propagate from one stage, generate and propagate from the previous stage, and then you have your 2 outputs, which is actually 4 outputs because you need to do all of these things at the same time, right? You want to get generate and propagate out this way and generate and propagate out this way. So that's called merge, right? We're merging these two adjacent propagate and generate ranges so that we can continue our calculation and do these things correctly. The other thing that we can do is that we can simply just feed it through, right? So the idea is that if we have some input from somewhere, you can just spit it out again, and we're going to do the same thing here. We're going to duplicate this output and send it in 2 different directions so that it can be used in multiple ways. So this is called feed through. The other thing that you might see, you can imagine that this arrow is not here and it's just 1-to-1. I've been calling that pass through because it's just passing it through one bit as opposed to feeding it to another stage here. So we more or less have 3 different kinds of bubbles, if you will. We have the merge stages, which is where the actual logic is happening. We have the feed through stage, which helps us actually route the signals where we need to go. And then we just have a pass through stage, which is literally just a simply connected 1 arrow in, 1 arrow out, just sending it beyond the bit here. So if we were to take this representation and then draw it as kind of a graph, what we're doing here is representing a ripple carry adder as a parallel prefix diagram. So this is a 16-bit number here, just to demonstrate. And let's just say that we're working with these 4 bits right here, right? So this is our 4-bit number. This is where we're starting. We have our half adders out at the front here that are calculating our generates and propagates, and then we're feeding these in through like this. So you can see that these 2 are a pass through. This one is a feed through. This one is a feed through. This one is a pass through, this one is a feed through, and this right here is merge. So what we're doing is we're taking the information, the generate and propagate signals from the previous bit, we are merging them together with the generate and propagate signals from this bit, and we're using that as our output to then go to something new. And if you remember from the ripple carry, that's exactly what we're doing, right? We're doing the carry calculation once, then we're moving to the next bit and doing it again. And then once we've done that computation, what this red highlighted box here means is that these bits are all set. We are confident in that this is what the final value is for this bit. So we could take this original propagate signal, XOR it with the signal that's coming out right here, and we're all set. We know that that's good. So when we represent the ripple carry adder, what we're seeing here is bits on the horizontal axis and number of stages, which is effectively time, on the vertical axis. So as you can see, if we're just doing one by one here, we have this big diagonal line that goes all the way down from bit 0 to bit 15, and that's a huge amount of ripple that has to happen there. So it's just going to be continuously going down and down and down, and that's what's actually going to take up a ton of time. You can see here that it's going to take 16 stages essentially for 16 bits, which is a lot of delay. So the performance parameters of parallel prefix in the real world is the number of black dots, which is the merge logic, right? So this is the number of things that are actually happening. And in the real world, we care about this because we have a limited amount of space on our dies, and it directly determines the circuit area. And the larger the circuit, the longer that it takes for signals to go, etc. The next thing is the number of stages, which determines the critical path, and therefore the longer the critical path, the longer that the thing actually takes to compute. And here's another big thing in the real world is maximum fan out, which is how many inputs are driven by a single output. So the idea is that if you have, essentially, if you could imagine this stage here driving multiple of these, right? If we connected this output to multiple inputs, in the real world, that's going to cause issues for us because we have real electrical signals that are doing real, I don't know how to describe it. It's a real signal, right? So that means that there's resistance and degradation and noise and all of these other things that have, impose their own will onto these signals. It makes it harder for them to actually work. So when we're doing real world design, we care immensely about the fan out because in the real world, that determines how long each stage actually takes. And then the more connections, the higher the delay. So what does this look like in Minecraft? Well, the number of black dots, the circuit area, is still a big deal, right? If we want to make something relatively compact, we have to be careful about how we do this. Now, in normal Redstone, this would not really be that big of an issue because Minecraft is an infinite world, and as long as you have the correct chunk loading in place, you can build something as big as you want. Obviously, lag and real, other Minecraft stuff comes into that. But like, if we're thinking about this from a pure perspective, the circuit area itself is not directly the problem. However, I use observer logic, which means that you can't really just send signals wherever you want, right? I use Rails, which means that everything needs to be in a straight line. And if I want to change that for being a straight line, that means that I have to use an observer or a piston of some kind, which adds delay, right? 2 game ticks of delay every time I want to do anything. So circuit area does kind of matter for this. What matters much more than circuit area is the routing that has to be done between these stages, right? The routing between merge stages and feed-through stages is the thing that's the most important. Number of stages is incredibly important to us as well in Minecraft because this is what we're trying to do, right? We're trying to reduce the overall amount of delay that the machine takes to do its computation. The number of stages is going to directly affect this, right? This is the largest contributor to how long the machine is going to take is how many stages it has to do. Now, fan out is the one where Minecraft makes this a lot of fun because fan out, we have a very direct limitation, but not in the same way that we do in the real world, right? In the real world, if you have one output if you have one input being driven by one output, you're going to get, everything is going to be fine. If you have 2 inputs driven by only one output, there's going to be some equal degradation to each of them, obviously depending on the geometry. But every subsequent input that you add that's driven by that same output, they're all going to degrade the same amount, and it's going to continue to degrade as you add more and more and more until you get to somewhere where it doesn't work. Minecraft is, if you can imagine that as like a gradually falling line, Minecraft is like a step function, right? There is no degradation of a rail signal between the first rail and the ninth rail, right? It's all on. And if you think about this from a binary perspective, obviously Redstone does have this, right? Redstone does have fan out issues because the signal strength decreases as the wire gets longer, which is actually pretty neat. But if you're thinking about Redstone just from a binary perspective, right? If you're imagined to put a repeater at the output, same thing applies, right? It's either on or it's off, right? There's none of this weird fan out stuff that we have to worry about. However, there is a maximum limit for each of these things, right? Redstone dust can only travel 15 blocks and rails can only travel 9 blocks. So for us in Minecraft, fan out is less about the number of inputs being driven and more about the size of this relative to the medium that we're using here. So for us, that's rails, which means that we want to be careful about how these things are laid out. So in fact, the issue that we have in Minecraft with fan out is more akin to the issue that we have with the number of merge operators in the real world, right? It's more about the circuit area. Whereas the number of black dots here is actually much more to do with the routing of signals than the actual area that they take up. So just to summarize, in Minecraft, what are the 3 parameters that we care about? We care about the ease of routing, the number of stages, and the size of the machine with respect to the maximum length that different signals can travel. So, jumping back to the real world, as you can see, we have this nice bubble diagram. We have a whole bunch of different connections that we could potentially make, right? You can think about every pair of these bubbles or more as a possible connection that you can make. So, there's a lot of smart people in the world that have come up with some brilliant designs for how you can do this systematically, and there's a whole bunch of different ones. So, this is the Sklansky architecture, which says that we're going to do each of these things pairwise, and then we're going to do them 2 by 2, and then 4, and then 8. You can kind of see there's this self-replicating business here, where we're doing the same thing across multiple bits at the same time, then we're merging those together in one big shot, we're merging those together in one big shot, and then we merge them all together. Then you could do something that's called a carry increment adder, because here we're doing 1 merge, then 2, then 3, then 4, then 5, and so on and so forth. And we have these chains here that actually get us prepared for that. Brent Kung is a little bit more complicated. We're doing a gap of 1, then a gap of 3, then a gap of 7, and we're doing a whole bunch of different routing here. Very complicated to make sure that everything works. You can see that we've got kind of this weird merge thrown in here. And this is what's actually allowing us to do this calculation. Now, if you see how these outputs stabilize, because if you remember, these red bars are when the outputs are stable. You can see that we have 2, 4, 8, 16. Here we're going 2, 4, 7, 11, 16. Here, you just do a whole bunch of stuff for a while, and then all of a sudden you get your output, right? It takes a lot of stages. This is the Coggy Stone adder, which is very dense. You can see that there's a whole bunch of black dots here. We're doing a whole bunch of merges at the same time, and we're getting this basically done as fast as we possibly can. And then lastly, we have Juan Carlson, at least in the reference that I'm using here. These are the ones that are listed, which is kind of like a mix between Coggy Stone and a little bit, just like visually like Brent Kung and Coggy Stone. If you kind of mash them together, you get something that kind of looks like this. Still very systematic, right? You can see that there's kind of some self-replication here and then kind of an intermediate stage. And then we do all of our signal carrying and we do the final output here. So 1, 2, 3, 4, 5 different architectures. So these are the PPA architectures that you could imagine as a starting point, right? So the question is now, which one of these do I want to implement in Minecraft, right? Which one makes sense to implement in Minecraft? Because there's going to be one that's better than the others, right? Or at least we hope there is. So here's a performance comparison of the adders. And let's just quickly show what's being used in the real world. RC is very efficient. It's small and simple, but it gets slow. Brent Kung is a good compromise because Carry Lookahead is actually a modified version of Brent Kung. So it's a good compromise. Sklansky suffers from very high fan out. So in theory, it's very fast, but the fan out in the real world makes this a big issue. And you should already be thinking, this is interesting. And then Coggy Stone and Juan Carlson are very fast, but suffer from routing, right? So in the same issue here, you can see, holy crap, look at all these lines, right? What are we going to do? So here's just kind of the performance comparison, right? RCA, small and slow, but a minimum fan out. Sklansky is large and fast, but a high fan out. Brancung is kind of medium the whole way through. Coggy Stone is gigantic, but it's very fast and it has a very low fan out. And not only does it have a low fan out, it has the minimum fan out, which means that there's only one input being driven by each output. Juan Carlson is large, fast, and minimal. And then once again, carry increment is kind of medium across the board. So now the question is, excuse me, which one of these do we want to build in Minecraft? So let's go back to our 3 criteria here, and let's actually think about what they mean. So number of stages is pretty straightforward, right? The number of stages determines the critical path. So we want something that minimizes the number of stages. So if you look down here, what are the things that is the fastest, right? So here we're looking at speed. So that would be Sklansky, Coggy Stone, Juan Carlson. Now, what's the next thing that we have to worry about here? Remember, for us, the number of black dots is more about routing. So the biggest issue with all of these different designs, and in fact, we can just start here, is something that we are very unused to in Minecraft, which is diagonal lines, right? Diagonal lines and circles are our biggest enemies as Minecraft players. So when we're looking at this design here, we want to have something feed from one bit to the next and the next and the next. And the question is, how do you do that in Minecraft? Because you have a limited number of dimensions to work with. So in fact, let's jump back to the game here and just do a little bit of thinking here. So if I have this thing right here, which is my nucleus, right? This is my cell of some kind that we're doing the computation on. If I have an input here and an input here, I need a second input for my merge stage, which needs to come from somewhere over here. I need another output that needs to come from somewhere over here. So, intuitively, what does that mean? What it means is that we're going to have our inputs on one side here, and our outputs on the other side. And you can think about this as being essentially diagonal like this, if we're trying to represent what we're doing in game versus what we see in the PDF. That's more or less what we're trying to achieve here. And what we're doing is we're chopping it down by just going down to this. So here's our merge stage. That's all well and good. But now we actually have to fit this thing with multiple others, and we need to make it make sense somehow. So let's say for a second that I have my other merge stage right here, for example. Or let's take a more realistic case from based on what we saw in the PDF there. Let's say that we have them spaced like this. So we have a merge stage that needs to be fed by previous stages, and then this one maybe needs to get merged again down here. So the question is, we need to get this across here, and we need to get this across here. And that's all well and good, but now what happens if this signal has to somehow make it over here? Well, we could probably do that, but the question is, how do we route that effectively? And in fact, if you continue looking, you're going to find that it's very, very difficult to build something that is nice and compact, but still manages to make it work in some way. So that's actually what I started with, is this kind of topological analysis, trying to figure out how the heck am I going to get these signals to work the right way here. So this is essentially the very beginning of the PPA that I decided to design. This is the very first step in building it. So you can see here that I have propagate in, generate in, propagate from the previous stage, generate from the previous stage, and then my outputs were nominally going to be right here. So the question is, how the heck do you make this work? So now, one of the things that I haven't described yet is what's actually happening in these merge stages, which is going to be important to note. So for the propagate signals, let's see if I can find a good place to describe this. That's jumping ahead a little bit. So I guess we'll just talk about it, right? We have these two propagate signals and we have these two generate signals. And we're doing something like this. For each one, we need to merge them together. So the propagate signals are getting ANDed together. So the output of this propagate signal is the input ANDed with the other input. The output of the generate signal is a little bit more complicated. It's doing an OR operation with the two other signals here. And I will just do a quick double check to make sure that I tell you exactly the right answer. Give me just 1 second here. Something I should have prepared for. Yes, okay. So when we're actually looking at these signals here, what's happening is that the propagate signals are being ANDed together. So this propagate here is this propagate and this propagate. So PI preview, we'll just bust out the signs, why not? Don't quite have enough room on the sign here. But the propagate out is the propagate and the propagate previous. So we're taking these two signals and we're ANDing them together. Now the generate signal out is going to, I'm just going to put this on here. Remember that this is both propagate and generate. This is both propagate and generate. So the generate signal out is going to be this. So what we're saying is that we're going to take the propagate signal and the previous generate signal, which is going to be coming in from one of these two here. It's going to be coming in from over here. We're going to take those two things and them together, or we're going to use that generate signal as well, which is kind of what you saw here in the original calculations here for stuff like the carry lookahead. So if we go back to the carry lookahead here, this is more or less what's happening. We're having the generate from the previous stage and the propagate of the current stage, or the generate of the current stage. And that's exactly what's happening here. We have the propagate and the generate of the previous stage, or the generate of the current stage. So it's the same exact thing here in Minecraft. Propagate, generate previous, or generate. And that's what we're working with here. So now we need to fit two AND gates and an OR gate somehow crammed into here. And just as a quick recap for what these things look like, an AND gate is going to look something like a piston moving a block and an observer pulsing into that block, right? It's more or less basically using the piston extension and having these two things synchronized at the same time. So that whenever we see a piston, we think AND gate. OR gate is just two things that are, next to each other, right? So this was my first idea, was to have propagate, generate, propagate, generate, propagate, generate, propagate, generate. So you can see here's one AND gate, and that would give us our two outputs here. And then we could get the generate in and do that here. Here's our second AND gate, and we can use that with the previous one. But then, oh no, we run into signal routing issues because this one could get powered here, but what the heck do we do after that? So I adapted that a little bit, and I originally even sacrificed the idea of doing a one-wide tileable design just because I thought it couldn't be done. I thought there was no way that I could make this happen. So I resorted to something that looks more or less like this, which is kind of a grid of all of the merge stages put together, trying to figure out how it works. So then I realized, that's probably not going to work. What if I try and stack the signals on top of each other? So we have generate and propagate that actually just continue all the way through. So what I was thinking of is essentially a system that looks like this. Is that at each point we have more or less a signal right here and a signal right here, which is our generate and propagate. And then somehow we interleave this with the previous stage and the output. And we get some kind of topology that more or less looks like this. So that we have our inputs, input 1, input 2, and then both of the outputs here. So I wanted to find something that roughly resembles this. Sorry, I got to pause to take a drink of water here. I've been talking for a while. Oh, so we want something maybe now that looks stacked on top of each other. So you can see here, once again, we got the two AND gates, an OR gate somewhere in the mix. We're trying to figure out how this is going to work. And then I realized, well, crap. If this is what I'm trying to do, right? If these are my inputs and these are my outputs, I don't know if this works geometrically, because if we jump back to the PDF here, I was trying to do Kagistone. That's where I started, because Kagistone is the one that's kind of well known. And the question is, okay, we have multiple signals crossing over the space of 1 bit here. How the heck am I going to do that in Minecraft? And what I realized was more or less you can't, or at least not in the constrained way that I'm doing things right here. There just seems not to be a good way to get things next to each other, or rather through each other with multiple things. So I had a change of heart. Excuse me, you can't see my screen. I was looking here and I was thinking, okay, if I have an input coming in here, an input coming in here, generate and propagate, and I need to get multiple of these things across, you know, if I'm doing my logic in this space right here, how the heck do I get one line, let alone 6, all the way across here? And I had no idea. So I went back to the drawing board and I said, okay, Sklansky, Kagistone, or Juan Carlson. Juan Carlson has the issue where we have multiple crosses as well, although at the max it's only 4, which occurs right here. Kagistone is just a lost cause, right? There's no way that with the kind of architecture that I'm working with, I can make Kagistone happen. But I revisited Sklansky, and what did I see? Not only do we only ever have single crossings, right? There's only one cross here, only one cross here. What I also realized is that any time that you have a merge stage, it is always accompanied to the right by an empty dot, a completely empty dot, not a feed-through dot, an empty dot, or another merge stage. So what I realized is we don't need to do these diagonal lines here. We can just use this blank empty stage here and use it as a feed-through. So you can now think about all of these things becoming right angles. And in fact, what that allows us to do now is instead of having to worry about crossing over this line, we can just do it here and cross it across the stage, which means that we can power this guy and then send that signal this way and get all of these merge stages done. And if you look here for the 16-bit example, which is the maximum that I built in game, if we do that, this is kind of the maximum fan out, like we said that we happen. And let's count that here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Perfect for Rails. So at this point I was like, okay, Sklansky it is. Let's try and make this thing happen. So did a bit more goofing around. You can see now that I've kind of had this idea of the signals propagating all the way across and through, so that then when you can trigger all of these merge stages at the same time. So, okay, this starts to look good. It's 2Y tileable, but wait a second. I can make something that looks like this. And now we can actually go over to the demonstration area. If I were to show you my screen, just do a quick recap of that. I was saying, okay, this is not going to work. We need to do Sklansky. This is what we're looking at here. You can start to see the effect of, sending these things through the middle of the stage instead. And I realized that you can even compact it further, and that is what leads us to this. So these are the final different kinds of nodes right here. So this is what I'm calling a pass-through. This is just a super dumb input-output. So this is the propagate on top, the generate on the bottom. You're just flying through here with 2 observers of delay. Now, why 2? All of the logic gates that I've designed, and XOR, etc., are what I'm calling a 4 game tick architecture, which means that any gate and XOR are the 2 big ones, take 4 game ticks to complete. So for each stage, we want the delay of each stage to be 4 game ticks, right? That's the smallest that it can possibly be if we do all of those gate calculations at the same time. So the minimal stage delay is 4 game ticks. So this is our pass-through. Now this is our feed-through. And what this is doing here is this is doing that split operation. So we jump back here, you can see that we're trying to do this diagonal thing right here, but what we decided instead to do is we're going to do down and then a right angle. So that's the purpose of this device right here. So once again, we have our propagate and our generate inputs, and what we're doing now is we're outputting them to the side here, and in fact, just on the one side here. So we put that all together, and then we get to the master here, which is the merge stage. So once again, we got the propagate here, we got the generate here. If this is what our feed through stage looks like, we've got a propagate from the previous and a generate from the previous, which are going to be coming in on these rails respectively. And in fact, what I'll just do is shift the schematic over here so you can see what that looks like. So no interference between the two stages. They work perfectly together. In fact, we could even bring a pass through right here, and you can see that all of these stages will work together with each other in any kind of ABC tiling that you wanted to do. So we got the stages here, it feeds into the previous, and now let's look at the actual calculation that's happening. So as we said, we are ANDing the two propagates together. So here is our first AND gate. We go up here to the piston. The propagate is used for the piston here. The second propagate is coming in from the observer. Boom, there's our AND gate. And we're noticing now that we're only outputting on one face instead of two, because we're using these feed-through stages to basically turn the corner. So we only ever need to output it in one direction, because the feed-through stage is now what's responsible for actually doing our bidirectional outputs. So there's the first AND gate. Now, if you remember, the second AND gate is the generate signal, the propagate signal, and the previous generate signal, or the generate signal at the current bit. So here's our AND gate again. We're reusing that propagate signal. Then the generate signal from the previous bit is right here, triggering this rail right here, and the generate of the current bit is then ORed by going into this rail at the same time. So this whole thing right here, this AND gate is 4 game ticks, and then we have the same 4 game ticks down here. So what you can imagine is now, we can take these things together. We can, bring this guy over here. We can, do this, and then maybe this feeds another merge stage over here. We're doing multiple calculations. Or we can stack this next to each other, and you can see that all of this stuff lines up here as well. So an ABC tiled architecture that can work however you want it to make that happen. So let's start building it up based on what we saw in the PDF for Sklansky. So let's just do our first 4 bits here. So we have a merge, and then 2 merges next to each other, and these guys are all of a sudden going to become feed-throughs. This is going to be a feed-through, and then these 2 are going to be pass-through. So let's jump back to the game. Come on, OBS, please. Thank you. And we're going to see the exact same thing. So we've got a merge, and then 2 merges together. We've got a feed-through, and a feed-through, and then a pass-through. So this is exactly our 4-bit carry calculation logic for a Sklansky architecture. And because Sklansky is kind of self-similar, what we can do is we can say, oh, look, we're going to put that here once, and then we're going to put it again next to itself, right? So there are 2 of these here. And then we're going to take those outputs, and we're going to tie them all together in the 4-bit. So as a reminder, that's essentially, ooh, excuse me, what did you just do? I have no idea. But the idea is that we're going to then, once again, take this 4-bit, which you can see are the same, and then we're going to combine them again with another 4 merge stages, and we're going to get our 8-bit version. So that's exactly what's happening here. We're combining the 4-bit stages, and then we're adding the extra calculation for the 8-bit stage. And in fact, you can even do the same thing again to get up to 16. And if we were to look at the 16-bit machine here, you'd see exactly what I described, which is 1, 2, 3, 4, 5, 6, 7, 8, 9 blocks for the 16-bit machine. So this is the core of our carry. We stick that right in the middle of the machine, and all we need to do now is we need to add our pre-processing and our post-processing. So the pre-processing here is that first half adder, the XOR and the AND gate. This is really cool. I'll get back to that. And then on the output, we have that XOR gate that gives us our sum. And remember this, we have the same issue that we had with the carry lookahead adder, whereby we need to shift these bits over by 1. So I came up with another ABC tiled way of essentially shifting these over. So this one powers here into the block. This one powers here into this block, which goes here. And then the third one goes directly down into a block and then comes up. And you can ABC tile this across. So let's take a look at this half adder, because this is actually incredibly clever. So if you look at this from the side and you're familiar with the architecture, you can immediately spot this right here. You say, okay, yeah, this is the XOR gate. So now my challenge to you is spot the AND gate, because this is a half adder, so it has an XOR gate and an AND gate. Where is the AND gate? So the AND gate is actually right here. I am reusing one of the XOR pistons to do the AND operation, because if we think about what's happening with those two gates, I don't want to fly all the way over there. But right, when we're looking at the XOR gate, how does the XOR gate basically function, right? The idea is that we have two cross-connected pistons here, each with blocks. And the idea is that we have observers that are going right through here. And we have a rail line that's connecting in the middle. And the XOR says that if one of them works, then it goes. But if both of them are on, then it won't go. So they are cross-connected, right? So this observer also triggers this piston. So this one will go, and then it'll push this piston out, and it won't work. So for an XOR gate to work, we want the piston in the default position here, right? If it's out extended here, that means that we don't have what we want. However, the AND gate is the opposite, right? The AND gate works by having the block extend and then use that to complete the signal. So those are actually two opposite things. So we can use this individual piston to be both part of the XOR gate and part of the AND gate. So we trigger this signal, this AND gate, with the bottom signal here, which is responsible for sending a pulse to this piston here, and then therefore also using this XOR. So what we've done is we kind of melded the XOR and the AND gate together. And as a side note, this is one of the reasons why I really like observer logic, because this is kind of getting into like the VLSI equivalent of Minecraft. We're not dealing with individual gates. We're dealing with a substrate and a whole bunch of semiconductors, and maybe this is a transistor, maybe it's not. And the way that we throw all of these things together is kind of neat. So essentially what's happening here is that this piston is functioning as both part of the XOR gate and the AND gate in opposite states. So we can actually combine those two things together right here. So this is our generate signals, this is our propagate signals, and if you recall, the propagate signals are then XORed with the original propagate signals are XORed with the final generates. So you can see here that this is actually the next stage of propagation here for the propagate signals. But those are not being used at all. You could probably remove this top half of the machine right here to no effect at all. But I just kept it because then when you go and paste it for a 16-bit version, it's nice to have it there. So you take those original propagate signals, you jump them over the top, and then you do the final XOR. And when you put that all together, you can do it for a 16-bit version too. So let's do a quick summary of timing. As I said, that 8-bit version is 22 game ticks. So we've already established that we have a 4 game tick architecture to which we do all of our calculations, and we have 22 game ticks for this machine. So let's think through this. Pre-processing and post-processing are each 1 gate delay, so that's 4 game ticks apiece, so that we're up to 8. Then for this calculation of Sklansky for 8-bit, we have essentially 3 stages before the output is solidified. So 3 times 4 is 12, so we're up to 20 now. So the absolute theoretical maximum fastest that you can go is 20 game ticks based on this 4 game tick architecture, because you have 1 stage of pre-processing, 3 stages of carry calculation, and 1 stage of post-processing. But I said 22. Why is it 22 and not 20? That's because of what I talked about earlier with routing issues with Rails, right? If you want to move between blocks, necessarily you have to incur a delay. And that's what's happening here. That last 2 game ticks is coming from these observers right here that are responsible for doing the shifting to get the gates lined up for the XOR. Unfortunately, there's really no way to avoid this if you want to keep everything nicely stacked like this, because either you're shifting over the generate signals or you're shifting over the propagate signals on the top. So there has to be a shift that happens at some point, and this seemed like the best place to put it because you'd have to deal with all this stuff coming down over the top. So we lose our 2 game ticks here to do this calculation, and note that the propagates also have to be synchronized, which is why we have this extra observer here, which is standing in the same place that this is delay-wise. So that is a probably 2-throw explanation of parallel prefix, addition in both the real world and Minecraft, some of my thought process behind what goes into designing these machines. You can see that this kind of looks like what you almost expect this to look like, just a little bit wider and less efficient. And the importance of doing iterative design, right? Pick your mark, take your shot, see if it works, and if it doesn't, go back to the drawing board. If it does, make it a full build and then post a YouTube video on it. So cool. All right, well, that's what I have for you today. Thank you very much to ETH Zurich for putting out that PDF. It was immensely helpful to me. I referenced it a lot during the build. And if you have any questions, as always, please let me know. I'd be happy to answer. But for now, that's all I've got. So thank you so much.